since we know that the fixed point numbers aren't adequate enough, we're going to use the floating point numbers. Alright, the floating point numbers, for example, you have this particular binary. For example, you have a very large values. You can actually write in terms of this form. Alright, so over here you let the decimal over here to be over at this side. You see, so you bring it all the way times 10 to times 2 to the power 7. Alright, so you shift the decimal point, alright, to this point. Alright, same thing over here, you shift the decimal points. Over here you also shift the decimal points. But dependent on how you shift the decimal points, alright, the values over here at this particular first value is always 1. Alright, so your purpose has to be 1. Okay, so the first bit has always be 1, so please take note of that. Alright, and then the power 7, it all depends on which power you want to sub in already lah. Okay, so normally you can represent your things as this form. Alright, this is called the floating point numbers. Alright, so you can represent your numbers in this way. Alright, and if you go furthermore, you look at this thing, -1 as this thing. I don't even know what the hell, but S signify sign, which is plus or minus, fraction F, and exponent I think is E, but I think the sign is actually the plus or minus lah. But anyway, let's continue and see how it goes. Alright, so the sign S is equals to 0 if it's positive, if it's equals to 1 then it's negative. Alright, exponential is equals to negative 126 to 127. Alright, for a 32-bit system, I think. Didn't say it. But anyway, the fraction is F is equals to 22-bit times 2 to the power negative 1 plus 21-bit times 2 to the negative 2 plus 1 bit plus 0 bit. Alright, so in total there is quite a few stuff. Oh, okay, so we are talking about 23 bits, for example. If you're talking about, okay, so we are talking about single precision, we are talking about this. So they actually use this thing as an example. So for single precision, how you use is, for example, your S is 1 bit. 1 bit, if it's 0, tells you that it's a positive number. If it's 1, then tells you it's a negative number. Okay, so this is how it is being words lah. Okay, so S then times 1 plus F is a fraction. Your fraction is 8 bits. Alright, so 8 bits can represent -126 to 127. Alright, this is how, your F, okay, sorry. Your fraction can be represented in this form. Okay, so your fraction can be represented in this form using 23 bits. Because fractions, as you know, is a tough thing to do. So you can use a fraction to represent your stuff. And lastly, your exponents can be written as your 8 bits. Alright, so -126 to 127. I don't know what the hell is it. I think it's 1111 1111. If it's an 8 bit, I think it's 255. Alright, so if you have plus and minus, you have the two complements, if you still remember. So you have 127 and then you have 126 -126. Alright, so if you add up together, you have 255 also. Alright, so for example, if I were to add 127 plus 126, okay, what do I have? 127 plus 126, I have 253. Sorry, I have 253. Okay, somewhere there lah. Alright, because in between there is a 0, right? So for example, if you still remember all the way back, over here I have 16 digit. Alright, this is a 4-bit system. I have 16 digit. Alright, but the highest is +7, the lowest is -8. So in our case, for the 8-bit, the highest is 127, the lowest is -126. So in between there is a 0 over here. Alright, the 0 actually counted as 1 bit. Alright, so in all together, this over here is 8 bit, over here is another 8 bit. So if this 0 over here, this actually belongs to over here, I think. So it's actually 128 bit. plus 126 bit, you have 254. Alright, and I think the last bit I don't know for what one, but anyway, at least you get to see how this is being utilized over at this side. Okay, so this table over here, alright, helps you to decide your stuff. Okay, and therefore over here I'll just repeat again so that you fully understand, is that this equation finally I know what it is. So minus 1 over s is actually this one, alright, your sine s. So if it's 0, then this thing over here will becomes 1. Alright, if it's 1, then this thing over here becomes negative 1. You see? So therefore it is pretty smart way. So you can change your sign plus minus using your positive or negative. Alright, 0 or 1. So you use a 1 bit to change your sign. So for your fraction part, your fractions, because your fractions need to be more precise, so therefore in other words you need a lot of bits. So it takes in 23 bits, as you can see. So the fraction wise is a little bit more tedious lah. So therefore you can have bit 22 all the way to bit 0. So this whole stuff over here takes in 23 bits. Okay, well, exponential can take in negative or positive numbers. So it's a signed exponent. It's a signed integer for your exponential, because it has positive from 0 all the way to 127 and all the way to negative 126. So in total it should be 255 bits, 255 values lah. Okay, so to speak lah. Okay, because 8 bit is 256 minus 1, which is 255. By right, over here at the exponential, you should have 255 possibility numbers, alright, or 255 possible numbers, where the 255 possible numbers are all this from minus 126 to 127. Okay, so yeah, this is the way. So your single precision, you use a 32 bit in this manner. So 1 plus 8 is 9 bit, 9 bit plus 23 is total 32 bits. Okay, so so the largest you can go is 3.4, the smallest you can go is 1.18, 10 to the negative 38. Alright, so plus or minus is okay because it's also only determined by 1 bit only over here, but the magnitude itself, the largest is this, the smallest is this. Okay, so a 32-bit system can actually help you to get the largest value of this, smallest value of this. Okay, using all this information that you can see. Yay, I finally understand what it means. Yay. Like macam muni. So now this is for single precision. Alright, at least it's, to a certain extent, it's still quite precise. For double precision, you're going to take in 11 bits for your exponential, so you're going to have many values, and 52 bits of your fraction. So it's getting more and more precise. That's why it's called double precision. Alright, and therefore the largest you can go is to the power of 308. This is not 38 already. So you see, it's way gaylord. Alright, and then unless if you have a double extended 80 bits, macam, this is way high already. You see? So therefore this is something for you to take a look. Or at least you fully understand this part. I'm very happy. Before I go further, 22 times 2 to the negative 1 is what? Bit 22 is telling you whatever bit that you are looking at. Alright, times 2 to the negative 1 is actually 2 to the negative 1 is actually half. 2 to the negative 2 is actually 1 quarter. 2 to the negative blah 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 is actually 1 to the power of 2 to the 22 lah, if you were to say so. So it will be a very precise number. Alright, all the way. So a 32-bit system can be represented in that. So and just to say is I'm doing in terms of the fraction now. Okay, so I'm just trying to tell you that the fraction is calculated in this manner, while the bit 1, bit 0 is, I think, is just to tell you that whatever bit you're talking about, if this bit can be 5, can be 4, can be any values. Alright, because it is just some values multiplied by this thing. That's all, nothing much. Okay, yeah, so you need to understand that. or itself this is a bit. So this bit is actually 1 or 0. Okay, so this bit 20 second, I think this is a better way I don't want to say lah. So this bit 20 second is 1 or 0 times 2 to the next one. If it's 0, then this whole thing will become 0. If it's 1, then you'll take in value. So bit 21 over here is 1 or 0 again, and then bit 1 is 1 or 0. So each of the bit is 1 or 0. Okay, and later on, now therefore hopefully you can understand now all these things. So now we talk about exponential e. Alright, e, just now we say that it's from 1 to 7 all the way to 0 and then minus 1 to 6. Alright, we say that overall this should be 255. But if you in the end, if you 1 to 7, if you take 1 to 7 plus because 0 is by itself is 1 bit, and then plus 1 to 6 bit, you have 254. The last bit is actually to define a special number. If e is equals to 0 and f is equals to 0, is defined as 0. Alright, if e is equals to e max, f is equals to 0, is defined as infinity. Alright, I don't know how it goes, but just for you to take note of lah. Okay, so if it's this e is equals to e max and f is not 0, then it's not a number. Alright, I don't know why. If f is 0, so bit times 2, so this bit is either 1 or 0. So if this is 0, this isn't any number at all. Wait, if f is not 0, it's defined as not a number. If it's not a number, then it is a fraction. Okay, so if f is equals to 0, alright, then 0 times this, then 2 times 2 power of 0 is actually 1. Alright, and anyway, this is special coding. So the special coding tells you that if s equals to 0, it can be either defined as 0 or infinity. Alright, so you need to own self go and define. So for example, if the bit, because 2 to the power of 0 is this one, so if the bit is 1, then it's considered infinity. If the bit is 0, then it's considered 0. You see, because f is equals to 0, or it's over here 2 to the power of 0. Your f is equals to your bit times your 2 to the power of 0. So your bit is 1 or 0, correct? So this thing is 0, but it has two possible values. Either it is 1 or either is 0. So if it's 1, then you're talking about infinity. If it's 0, then you're talking about 0. Alright, it's just equals to 0. So therefore, if let's say for example, if my bit is equals to 1, then this fraction is actually infinity. Okay, so if my bit is 0, then it's equals to 0. That's all. Okay, yay, at least something I know. So e equals to 0, it's 0 by itself at some point is 0, right? So all the way to negative 1 to 6, all the way to 1 to 7, and if it's 0, then it's considered 0 lah. Okay, and then if e equals to e max, so which is 1 to 7, if you say so, then it's considered infinity because it's a very big number. Okay, yeah, so I think yeah lor. And it's not a number also because it's infinity, but infinity is just not a number at all. Okay, so I think yeah, these are the little stuff that you may want to know lah. Alright, so I think I did a fairly good job in explaining this thing, and I find it kind of nice. And therefore lastly, this page is just to tell you that the difference between single precision or double precision, or this table over here, 32-bit versus the 64-bit, is that you can model your system more precise because of the decimal points. Over here, for example, 1 plus 0, alright, you can actually rewrite as 1 plus 2 to the negative 23, because the highest exponential is, the highest fraction is 2 to the power of negative 23. Alright, so therefore this thing over here, if you write it out, is 1.00000 all the way to 1. Alright, So you can go all the way to negative 23 decimal place, some sort of the meaning lah. Okay, but however, if you talk about double precision, you can go to 1.0000000000000 all the way negative 52 power of the decimal. So you can model a very precise value very vividly, very clearly. So this is the difference between the single precision and double precision. So you need to know lah, is their precision. Alright, so single precision compared to double precision is more precise because it has more bits to formulate the decimal points. You see, 52 bits is 23 bits. So once you see this table, straight away you know for the sign, negative or positive is 1 bit, then e is the exponential f is these things. Alright, so you can also memorize this equation. Alright, minus 1s times 1 plus f times 2e. Okay, I think this is pretty good thing for you to memorize also. Yeah, so I think this is by far what I can do for you, and that's it. So see you in the next video for the last part. So we are somewhere here already. Alright, we are at this point. We have finished all this already. So we have only left this part to go. So I shall see you soon.